In the last few lectures, we had been taking a look at various op-amp circuits. And as I have already said before, the number of possible circuits and number of different kinds of circuits is way too big for us to be able to cover them all during the semester's course. And we are only devoting a few lectures to this. Anyway, let us continue with the topic of advanced op-amp circuits. The first class of circuits that we are going to talk about in today's lecture are the active rectifiers. So now you might very well ask, why do we need to take a look at rectifiers again, given that we have actually extensively dealt with different kinds of rectifiers when we were discussing diode circuits? To explain that, let me just point out or remind you of the kind of output an ideal rectifier should have. If you have an input signal which goes up and down, both positive and negative like this, the output should only pick out the positive cycles from the input, and whenever the input is negative, it should give you 0 as an output. So what you really are aiming at is a behavior which goes like this. VO of time is equal to VI as a function of time if VI is greater than 0, but is 0 if VI is less than 0. This, of course, is the half-wave ideal rectifier behavior. Now, as you all know, we can easily implement a half-wave rectifier using a diode and a resistance combination. In fact, this is a very simple circuit that will do the job for you. However, if you had an ideal diode, this would really give you the ideal response that you wanted. But a real diode is not an ideal diode. So, for a real diode, the current cannot be arbitrarily big in the forward direction with no voltage drop across the diode whatsoever, and there is a tiny but non-zero current in the negative direction, in the reverse bias direction. So there is a minus IS, the negative value for the reverse saturation current in the reverse direction, and you can approximate the behavior of the diode in the forward direction by saying that there will be some voltage drop V gamma across it, and V gamma typically is of the order of 0.6 to 0.7 volts, depending on the kind of material your diode is made of. So what happens when you feed a sinusoidal signal, say, to a diode resistance combination like this? You actually get a reasonably good approximation for a half-wave rectified output. The ideal output here is the line in purple, the thin line, and the blue line gives you the actual output that you get. As you can see, that there is a negative output voltage given by IS times RL in magnitude. Typically IS is very tiny, so IS times RL would usually be small unless RL is huge. But this is, of course, a deviation from the ideal behavior. What is perhaps more important as a deviation from ideal behavior is the fact that the forward bias diode actually drops a reasonable amount of voltage, not a very tiny amount of voltage, around 0.6 volts or so. And so the output is actually shifted below what the ideal output should be like. Now, if you are using your rectifier for power supply purposes, typical voltages and currents involved are quite big. Compared to that, IS or this V gamma are very, very small quantities. And as a result, this deviation from the ideal behavior is not really much of a concern. However, you can often use rectifiers not for power supply purposes, but for some precision calculations maybe, or figuring out some precision data dealing with an input signal. And in such cases, the input voltage peak or the currents involved may not be so huge that we can ignore these deviations. So, for high precision applications, these deviations from non-ideality are sometimes unacceptably large. So what's the solution to this problem? The solution to this problem is using something called an active rectifier. And since we are discussing op-amp circuits, it's easy to guess that our active rectifier circuits will actually involve an op-amp in some way or the other. So this is the circuit diagram for the simplest kind of active rectifier, which just uses a single op-amp and a diode resistance combination. Note that the resistance that we have here, marked R, is actually connected directly to the output. So this really is the load resistance which the rectifier will deliver its output to. And also note that the diode is sitting in the negative feedback path for the op-amp. Let me stress here that because we have deviated from the standard convention that the upper input terminal is the inverting one, we have deviated from that here. So we have explicitly marked the upper terminal as non-inverting. So let us try to figure out how this circuit works. Well, let's suppose the input voltage here is positive. Now, when the input voltage is positive, what happens is that the non-inverting terminal has a positive input. As a result, the output voltage is going to be positive. But if the output voltage is positive, the diode becomes forward biased. So, the feedback path is completed. Of course, when the feedback path is completed, the system will try to go into virtual ground, provided the op-amp can stay in the linear region while doing that. So what will happen is, since you have Vi here, you'll get approximately Vi here. In fact, well, approximately here is really closely Vi, because the difference is less than a millivolt, as we have already figured out before. So the output voltage, which is of course the point voltage at this point, is going to be Vi. So when Vi is positive, Va will be greater than 0, the output voltage of the op-amp. So the diode will be forward biased, and that will complete the feedback loop and ensure virtual ground, of course, as long as the output stays within the plus Vsat limit, and Vo will be exactly equal to Vi because of that. And at least for the positive half cycle, our circuit does behave like a rectifier. Note that this will happen even if Vi is tiny. Vi does not have to exceed V gamma or the current voltage of the diode for this to happen, because even a tiny Vi will be amplified by the amplifier to produce a substantial Va here. In fact, now that we know that the Vo is equal to Vi, we can go back and figure out that the voltage which the op-amp actually puts out, not the voltage output for the circuit, but the voltage output for the op-amp, is actually going to be V gamma plus Vi. That's because there's a drop of V gamma across a forward bias diode. So half of the cycle, at least for half of the cycle, the positive half of the cycle, this circuit does work as advertised. What about the negative half of the cycle? Well, in the negative half, what's going to happen is Vi becoming negative essentially makes Va negative. That cuts out the diode. As a result, the negative feedback path is gone. So this point, the output is directly connected to the ground with no other source of current. Remember, the op-amp will deliver or take in very little current from its inputs. What that means is when Vi is less than 0, diode being off, this would give you Vo of 0 volts. And what about Va? Of course, now that you don't have a negative feedback path any longer, there is nothing to prevent the op-amp from going into saturation. In fact, the op-amp will go into saturation, negative saturation in this case, and you're going to get minus Vsat. So this circuit does work the way it is supposed to. It gives you a positive output equal to Vi when Vi is positive. It gives you 0 output when Vi is negative. Now, this would have been all if we really had an ideal op-amp. But even op-amps, no matter how close they are to their ideal counterparts, are not really ideal. They have their own limitations. One very important limitation of the op-amp, which we have not talked about so far, is something called the slew rate. This is the maximum rate at which the output of an op-amp can change. Now, of course, the slew rate varies from op-amp to op-amp and depends on which kind of op-amp you're using. So, the ordinary kind of op-amp that you can buy off the market, the cheap version, let's say the 741 IC, which is the popular common op-amp that is used in labs all over the world, has a slew rate of around 0.5 volts per microsecond. So it takes a microsecond for the op-amp's output to change by half a volt. Now, why is that a problem in this case? Well, let's take a look at what the op-amp output does as the input to the active rectifier changes from positive to negative. Notice that as long as Vi is positive, the output is Vi plus V gamma. So when Vi becomes very, very tiny but still positive, the output is V gamma around 0.6 volts. So you have around 0.6 volts for Va when Vi is very close to 0. But when Vi becomes negative, again a very small difference from 0 but just negative, the output jumps to minus Vsat, which is around minus 12 volts. So you have a 12.6 volt change in the voltage, in the output voltage of the op-amp. The trouble is, an op-amp would take some time to carry out such a big change. Now, how much time? If you are using an IC741, this time is, 12.6 volts divided by 0.5 volts per microsecond, around 25 microseconds. The 25 microseconds might sound like a very, very tiny time to you. And it is tiny as long as your input signal frequency is small enough. But if your input signal frequency is somewhere of the order of, say, hundreds of kilo ohms, then the time period for the entire signal is of the order of tens of microseconds. So 25 microseconds becomes a huge time interval for this to work. So this circuit will work well enough for low enough frequencies, but for large frequencies, for which you might often want to use active rectifiers, this becomes not at all a tenable circuit to use. Of course, the 0.5 volts per microsecond limitation that I have talked about, the slew rate that I have talked about, is a slew rate for a standard op-amp that you can buy off the market. This is a typical value for 741 IC, as I have been mentioning. You can buy high-speed op-amps from the market, and op-amps which have slew rates which are much higher, let's say something like 100 volts per microsecond, are easily available. They are more expensive, of course. So if you really want to work at high frequencies, those op-amps would be a good choice. But they would, of course, cost more. But you have to remember one thing. Because of this slew rate limitation and because of the rather large jump which the op-amp output has to go through from plus 0.6 volts to all the way down to minus 12 volts, such an active rectifier will not really be a great choice for high frequency work, even using high-speed op-amps. As we will soon see, there are modifications that you can make to this active rectifier circuit which will make this a lot faster. But before we go there, let me just dwell on the topic of the slew rate a bit more. The slew rate actually is an important issue which can come up in other kinds of applications as well. For example, maybe you're just using an inverting amplifier and you're fed in a sinusoidal input and you expect that the output would be a nice sinusoid. That will be fine unless you went to high enough frequencies and or large enough amplitudes. Then what would happen is that the rate of change of the output voltage that a sinusoid would impose may be way too large for the particular op-amp that you're using. And then what will happen is that you're going to end up with a waveform which does not look sinusoidal at all. The waveform will end up looking triangular. Why? Simply because the op-amp cannot change its voltage at the rate at which the input dictates that it change. So it changes as fast as it can. So since it's limited by the slew rate, it changes at the slew rate. In fact, by feeding an op-amp a high enough frequency input voltage and looking at the output waveform using, say, a cathode ray oscilloscope or some such device, you can easily measure the slew rate. Let us now try to discuss a circuit that's going to overcome, or at least partially overcome, the limitations due to slew rate that our previous circuit had. So this is a rectifier again, an active rectifier, but there are some differences. Of course, as you can see, there are two diodes here, as opposed to only one in the previous example. But perhaps more importantly, you can notice that here, what we have done is we have connected the input through this resistance R to the inverting input of the op-amp, as opposed to the previous circuit where the input was connected to the non-inverting input of the op-amp. Now let us try to understand how this circuit will work. Notice that here you have two feedback loops and both of them have diodes in it. So let us try to see what will happen if Vi, let's say, went negative. If Vi is negative, what's going to happen is the output voltage, of course, is going to go positive here because of the fact that Vd is now positive. Now, if Va is positive, that's going to drive this diode D2 in the forward direction. So this is going to be a complete feedback loop. So the output is going to be connected back to the input via the diode D2 and of course through the resistance R. With Va positive, this D1 diode is going to be reverse biased, so D1 is going to be off. So what we have is D1 is off, D2 is on, or D2 is forward biased. So now, once you see that this feedback loop is connected, this really works like an inverting amplifier with gain -1. To see this in some more detail, let's just point out that as long as the op-amp is working in the linear region, you're going to get virtual ground here, which means the current through this resistance R is going to be Vi over R, and that current will not flow into the op-amp because negligible current flows into the op-amp, will not flow through this diode because this diode is reverse biased. It will flow entirely through the resistance R, causing a drop of Vi across R and leading to this output voltage here, Vo, being minus Vi. So Vo is minus Vi. And in addition, what we have is Va, the voltage that we are looking at as the output of the op-amp, has to be bigger than whatever this Vo is by V gamma, because V gamma is a drop across this forward bias diode D2. So as long as Vo or minus Vi is not too big, Va, which is Vo plus V gamma, stays within the saturation limits, this circuit is going to work fine, and you are going to get an output which is not equal to Vi but equal to minus Vi, at least for this half of the cycle. What happens for the other half of the cycle? Well, in the other half, when Vi is positive, remember Vi is being fed through R into the inverting terminal. So when Vi is positive, what happens is that the output Va goes negative. Now that Va goes negative, this diode D1 is going to be forward biased, and that's going to provide a feedback path. Once again, that's going to ensure virtual ground, and what you're going to get is nearly 0 volts here. But if you have nearly 0 volts here now, that will cause a current Vi by R to flow through the resistance R, but almost this entire current is going to go through D1. D1, the forward bias diode, is a much lower impedance path than the resistance capital R here. So the entire current through this resistance is going to flow through the diode D1. Nothing is going to flow through R, which means the drop across R is going to be 0, which is going to lead to an output voltage Vo of 0. Okay, sorry, I wrote it on the wrong side, so let's write it on the right side. So just to repeat what I said, if Vi is positive, D1 is going to go on, D2 now is off, and that means you do have a virtual ground here, the entire current flows through D1. As a result, nothing flows through R, and so VO, the output voltage, is going to be 0, and VA, the op-amp output, is going to be simply equal to the drop across the diode D1 with a minus sign, of course, so it's going to be minus V gamma. Of course, as you can see, there is no problem with saturation here, so the circuit is going to stay in the linear region throughout, unless, of course, the input is too big when it's in the negative cycle. So the upshot of all this is, this circuit produces an output equal to minus Vi when Vi is negative and equal to 0 when Vi is positive. And this is very, very close to the ideal behavior simply because the very tiny input voltages are sufficient to drive either D1 or D2 to forward bias because of the op-amp playing an important role here. In case you are wondering where this current goes when Vi is positive, we said all the current through this R goes to the diode D1. Where does it go after that? It cannot go through D2, of course, because D2 is reverse biased. What it does is, of course, flows into the op-amp. Remember, the op-amp has huge input impedance. Very little current will go into the op-amp from the input side. But it has nearly zero output impedance, so it can take arbitrary or at least reasonable amounts of currents in without any voltage drop being caused because of that. Now, of course, as you can see, this is a rectifier because it only allows voltage of one side at its output. But there is a small catch here. As you can see, the output, of course, is minus Vi. For negative Vi and 0 for positive Vi. So it's sort of behaving in the opposite manner to a standard conventional rectifier. If you want to make a conventional rectifier out of this, you can actually put in a initial inverting amplifier stage with gain minus 1 between the Vi and this circuit, which will cause the circuit to behave like a conventional standard rectifier, which gives you a Vi output whenever Vi is positive and 0 output whenever it's negative. Okay, that's fine. But how does this circuit really help in speeding up things? Notice that the output of the amplifier itself, Va, is Vo plus V gamma, that is minus Vi plus V gamma whenever Vi is negative. So when Vi has a very tiny negative value, it's getting close to 0, the output Va is actually equal to V gamma. When Vi switches over to the other side, when Vi becomes positive, the output changes to minus V gamma. So basically the op-amp amplifier output here actually switches from minus V gamma to plus V gamma, or the other way around depending on which way Vi is changing. And this change is a lot smaller than the change that occurred when the input was changing sign in the previous example. In the previous example, the output of the amplifier was changing from V gamma all the way to minus V sat. So more than a 12 volt change. Here the change is going to be from around plus 0.6 volts to minus 0.6 volts, or the other way around. So around a 1.2 volt change. Which means that the time it would take the op-amp to change its output that much will be 10 times smaller in this circuit. Or in other words, they should be able to work comfortably at 10 times higher input frequencies without compromising the ideal nature of the output. Both the circuits we have been looking at so far have been half-wave rectifiers. We might also want to have full-wave rectification produced using active circuits, and one such example is this one. So this is an example of an active full-wave rectifier circuit, and in order to understand how this works, let me just first focus on just the orange part of the circuit. If, for example, this end had been grounded, then what would have happened? If this end were grounded, let's say this purple connection really is not there, this end is really grounded, then it's easy to see that if this is grounded, that means you have actual ground here, virtual ground here, negative feedback path here, which gives you a gain of -1, and it's pretty straightforward to see that the output would be -Vi. What about the other option, if this end were open? Of course, if this were open, then no current would flow through this resistance, simply because there's no path for the current to flow. Remember, this connection is not there as far as we are concerned right now, and no current flows into an op-amp. So, no current through the lower R means no drop across R, which means the plus end would be at Vi. That means this end would be at Vi. And if this end is also at Vi, that means no current flows through this resistance. No current through this resistance either. So Vo will be equal to Vi. So in this circuit, if you forgot the lower part, if this end were shorted to the ground, the output would be -Vi. If this were open, the output would be +Vi. Now, this is exactly what is going to be achieved by this purple circuit here. So if Vi is negative, then this voltage here will be negative. A negative voltage to the inverting input would drive Vc, the output, to a positive value. And once the output becomes positive, this diode becomes forward biased, completing the feedback loop, and hence this will be a virtual ground scenario, which means Vc, this point being at 0 volts, this will be also nearly at 0 volts. Nearly 0 but negative, that's important, slightly negative. And that would mean this end would be also nearly 0 volts. So this terminal is grounded, which means A, the output is going to be -Vi. So this is what you are going to get. What about Vc, the output of this particular op-amp? That is going to become, well, if this end is at 0 and the forward bias diode is sitting in between, so Vc will be V gamma, the cut-in voltage of the diode. Okay, what happens if Vi is positive? If Vi is positive, what you have done is you have applied a positive voltage to this inverting terminal here, driving the output to negative values, and of course a negative value would mean the diode is now reverse biased, cutting off the feedback path, so this op-amp will be driven to -Vsat. And essentially, because this is detached, you have no path for current to flow, because the diode is reverse biased and op-amp of course will not take any current. So this becomes open. So as I explained before, if this end is open, Vi is going to be equal to Vo. So Vo is -Vi when Vi is negative, plus Vi when Vi is positive. Of course, this is exactly the behavior you expect from a full wave rectifier. The output is of course throughout positive and is really modulus of Vi. Now, you must have spotted that there is a problem with this circuit, and the problem simply is the fact that Vc, the output of this particular op-amp, the second op-amp, changes from V gamma to -Vsat when the input changes sign. So once again, this is going to be a slowish circuit. It's going to be sluggish because of this large change required, and slew rate limitations will put a limit to how high a frequency you can use this for. You can actually modify an active full wave rectifier circuit in such a way that it will be sped up a lot. Just like we had a faster rectifier discussed a while ago, I will leave that as an assignment for you to worry about. The next important class of circuits that we are going to talk about are filters, or to be more precise, active filters. And frankly, active filters may be the single most important application of op-amps in the industry today, and whole books have literally been written about this topic. And as always, we simply will scratch just the surface of this topic. To understand why active filters could be useful, let us recapitulate our basic notion of what a simple RC filter is like. So this is an example of a simple RC filter. You have a resistance R and a capacitor C. You feed the input to the series combination, you take the output across the capacitor. Of course, here VO by VI is simple, it's just the impedance of the capacitor divided by the total impedance. That's just the series potential division formula. And if I use that, I can simply rewrite this as 1 over 1 plus j omega CR, and identifying 1 by CR as a critical frequency omega C, I can rewrite this as 1 by 1 plus j omega by omega C. Notice that as the frequency increases, the denominator is going to become larger and larger in magnitude. As a result, the output voltage is going to go down with higher frequencies. At very, very low frequencies where omega is very much smaller than omega C, you expect this to be nearly 0, this j omega by omega C combination. So VO by VI will be nearly 1. So just to remind you, this is exactly what a low pass filter should behave like. Low frequencies are passed almost entirely. VO is the same as VI as omega goes to 0. And as omega increases, it should fall off with rising frequency. And in particular, when omega is equal to omega C, this ratio becomes 1 over 1 plus j, whose magnitude is 1 by root 2, which means that at omega equal to omega C, the output voltage has an amplitude which is 1 by root 2 times the amplitude of the input voltage. Since power is the square of the voltage, this is exactly what is called the half power frequency. Or if you are using the decibel scale, this is the 3 dB cutoff frequency. So this is often called the cutoff frequency or the 3 dB frequency or the half power frequency, depending on whatever application you have in mind. All of them mean the same thing. Now, while this is perfectly good as a low pass filter, it may not be good enough for the particular application you have in mind. Let me just try to give you a crude sketch of the output. Here, if you were to plot the VO by VI amplitude ratio against frequency, of course you have nearly 1 at low frequencies when omega is near 0, falls off to around 70%, 1 by root 2 at omega equal to omega C, and then it trails off. Okay, this is not really a very accurate picture, and frankly, I don't expect to be able to draw a very accurate picture by using freehand techniques here, but at least let's give it an attempt. This is what the VO by VI is going to look like as a function of omega. Now, for many purposes, this may be perfectly okay, except for one thing. After all, this formula is derived assuming that the entire current in this RC combination, whatever is flowing through R, flows through C. That means there is nothing further loading this circuit. Of course, in a filter, you have to apply the output to some load which is going to draw current from this. Strictly speaking, this result that we have is accurate only when we have a very huge impedance as a load or a very small load. So, the moment you begin to draw current from the filter, this behavior is going to get compromised a bit. Now, for many purposes, as long as you're using a huge load impedance and a sufficiently small source impedance so that the R here, which contributes to omega C, is not substantially affected, this circuit works fine. And if you were worried about having a large source resistance or a tiny load resistance, you might very well use buffers using op amps, which we have learned about, to isolate the filter from the signal on the one hand and the filter output from the actual load on the other. So that's one way in which op amps can be used to improve the action of a filter circuit. But sometimes the filter effect that we have due to this RC network may not be good enough. The ideal filter, say, should be something like this. It should produce VO equal to VI, so have a VO by VI ratio of 1 whenever omega is less than omega C, and ideally should give you VO by VI equal to 0 whenever omega is bigger than omega C. So this is ideal low pass filter behavior. And so the RC filter, of course, deviates from this ideal behavior quite a bit. Can you improve upon this? There are several ways in which you can improve upon this, and frankly, depending on what particular application you have in mind, different methods may produce more suitable results than the one I am going to try to describe right now. I can't really go through all the possible active filters that are used using op-amps, so we are going to just describe a very simple kind of notion which was forwarded nearly 80 to 90 years ago, which still happens to be one of the most common ways of having improved filter behavior. And this is the notion of something called a Butterworth filter. So what exactly is a Butterworth filter? A Butterworth filter essentially generalizes this expression. Notice that the VO by VI magnitude ratio that you have here for the RC filter is given by 1 by square, or let's talk about the square of this. That's 1 plus omega by omega C whole square. So if instead of this particular condition, which is essentially the power transfer ratio as a function of frequency, G of omega, instead of this thing, we would have loved to have this. Of course, G omega is 1 when omega is less than omega C and 0 when omega is more than omega C. That's the ideal case. But the Butterworth filter approximates this ideal behavior slightly better by having a transfer function. This is the transfer function for power, which is why it's a square of the ratio of voltage amplitudes, is given by 1 plus omega by omega C to the power 2n. N equals 1 would of course be the standard RC filter, but any higher n, typically higher integer value of n, would give you higher order Butterworth filters. And the higher the order of the Butterworth filter is pretty easy to understand. It's going to be closer to the ideal one. So, for example, if you were to look at n equals 2, that is 1 by 1 plus omega by omega square to the power 2, that is 1 by omega C to the power 4, you would have a behavior which goes like this. Go to higher and higher orders, you are going to get something which is steeper around the omega equal to omega C mark. You can try plotting this function using GNuPlot or any of your favorite plotting software to see how the behavior of this function changes as n rises. Now, I'm not saying that the Butterworth filter is the only filter which improves upon the standard low-pass RC filter behavior. There are many different kinds of ways of improving upon this behavior, and depending on your application, some other method may be more suitable. But for the time being, we are just going to stick to the Butterworth filter in our discussion. Now, let us try to understand how we can implement the Butterworth filter using op-amp based circuits. But before we go through the direct circuit implementation, we need to take a look at some of the basic mathematics behind this. And the mathematics behind this is basically the mathematics of complex numbers. So, class 12 level complex algebra is all that you will need to understand Butterworth filter properly. To understand the basic mathematics behind the Butterworth filter, what we need to do is take a look at the denominator here. The denominator, of course, is of the form one plus z to the 2n, where z which is omega by omega c, can also be extended to a complex number. We want to really look at the behavior of this function over the entire complex plane. as has been definitely stressed in your mathematical methods class, even if you're dealing with purely real functions, very often complex numbers are the easiest ways, provides the easiest way of finding out useful information about them. So this particular function, 1 plus z to the 2n, is a polynomial of degree 2n. So it can be factorized into 2n factors, z minus z1 into z minus z2 up to z minus z2n, where z1, z2, z2n are nothing but the zeros of this function. So the roots of 1 plus z to the 2n equals 0, or essentially the 2nth roots of minus 1. And a very simple amount of complex algebra would tell you that this is what the z's are going to be. Notice that k here runs from 1 to up to 2n and stops there, because if you go beyond 2n, you keep on repeating the roots over and over again. So these are the 2nth roots of minus 1. So what do they look like on the complex plane? Well, when n is equal to 2, we have 4 roots, or 4 fourth roots of minus 1, which sit on points on a unit circle, and you can easily check that each of these numbers, when raised to the power 4, will give you minus 1. Remember, raising a number with magnitude unity to a power simply means multiplying the angle by that number. So for example, if you take this one, the angle here is pi by 4. If you raise this to the 4th power, the angle of the 4th power is going to be pi, which is of course going to make this point land up right here and give you minus 1. Well, this is actually 3 pi by 4. So if you raise this to the 4th power, it's going to go all the way around and end up here at 3 pi. And so on. So n equals 3, there will be 6 sixth roots of minus 1, which are going to be placed on the unit circle. They're of course going to be equally spaced. N equals 4, you'll get 8 roots of minus 1, again equally spaced like this. And from this, it's rather easy to see that you have as many roots above the real axis as below, and these roots of course appear in complex conjugate pairs. So for each root above the real axis, there's another root the equal distance below the real axis, which of course is its complex conjugate. Remember, this quantity that you're looking at, which is the denominator of g omega, is a modular square of something. So because of these complex conjugate pairs that you have, it's actually very easy to see that 1 plus omega by omega c to 2n can be easily seen as mod square of half of these z minus zk factors. Because, or remember, omega by omega c is purely real, so let's just forget about the j for the time being right now. Omega by omega c being purely real, omega by omega c minus zk and omega by omega c minus zk is conjugate, are conjugates of each other. So multiplying them together would just give you the mod square of omega by omega c minus zk. Since the roots are in complex conjugate pairs, you can just take half of the roots, only the roots sitting on the upper half plane right now. So k going from 1 to only n, not all the way around, and you are going to get this expression. So this is the denominator in the form of a modular square. However, as you have definitely seen, in all our calculations, the omega really comes in because you have an omega dependence on the capacitor impedance, and their omega of course does not come in alone. It comes basically with a j thrown in. But j is a number whose mod square is of course 1, so you can easily just supply a factor of j overall, that means to both these terms here. And the mod square will of course stay the same. So j omega by omega c minus these will of course have the same modular square as our previous expression. So this is still 1 plus omega by omega c to the power 2n, the thing that I want. But these were roots of minus 1 sitting in the upper half plane. What happens when you multiply them by j? Let me remind you of your complex algebra Once again, multiplying a complex number by j essentially rotates it counterclockwise through 90 degrees. So what's going to happen is, while you were just looking at the upper half plane roots, after multiplication by j, they will turn round through 90 degrees and they will all end up here on this side of the real axis. So just as an example, the h omega is the quantity whose mod square is going to be g omega. So this factor here is actually 1 over h omega. So 1 over h omega for this particular example, for n equals 4, will have 4 factors. J omega by omega c minus this point, which is e to the j 5 pi by 8. Remember, this angle was pi by 8. When you rotate it through 90 degrees, it ends up here at 5 pi by 8. And you have 7 pi by 8, 9 pi by 8, and 11 pi by 8. 2 pi by 8 is a gap between each of these roots. That's again easy to figure out. The reason why I've written the middle two factors in orange and the extreme factors in green is simple. If you look at the two phase angles here, 5 pi by 8 and 11 pi by 8, they add up to 2 pi. So do 7 pi by 8 and 9 pi by 8. And it should be pretty easy to convince yourselves that that's going to happen in general for any arbitrary n. Of course, for n equals 4, you have only 4 such factors. For n equal to 12, for example, you'll have 12 such factors in 1 by h omega. And these factors will come in complex conjugate pairs. e to the j 5 pi by 8 and e to the j 11 pi by 8 are actually just complex conjugate pairs. So are these two. Remember, if you multiply these two things together, you get e to the j 16 pi by 8 or e to the j 2 pi, which is 1. So, unit magnitude numbers whose product gives you 1 are complex conjugates. So, these two things are complex conjugates, these two things are complex conjugates. The whole factors are not complex conjugates, by the way, because j omega by omega c, of course, is a purely imaginary quantity which is there in both the terms. However, exploiting the fact that the phase angles here are complex conjugates, you can easily multiply them together pairwise, the green brackets with the green brackets and the orange brackets with the orange brackets. And it's easy to see that multiplying, say, this with this will give you 1 plus 1. This with this will give minus omega square by omega c square. And multiplying this with this and this with this will essentially give you j omega by omega c times twice the real part of this. So twice cos 5 pi by 8 for this factor. For the orange ones, you'll get 2 cos 7 pi by 8. Okay. So if n is even, you have such even number of roots here, complex conjugate pairs as I explained, and you will end up with quadratic factors like this. This factor here is called in this case, a fourth order Butterworth polynomial. Of course, for a general n, you will have an nth order Butterworth polynomial, and this is a product of quadratic factors like this. Well, if n were odd, then in addition to all these roots, which are complex conjugate pairs of each other, you have one more root sitting exactly at minus 1, which is its own complex conjugate. So you will have an extra factor of 1 plus j omega by omega c from that term. So for even n, h omega is a product of n by 2 quadratic factors. For odd n, in addition to n minus 1 by 2 quadratic factors, you have an extra factor of 1 plus j omega by omega c. To understand this a bit better, let us take a look at one more example. This is for n equals 7. Of course, here 1 by h omega will have 7 factors, 7 linear factors, and if you group up pairs of factors in the way that we just illustrated, you will get 3 quadratic factors, this, and this. In addition, you will have one more extra factor of 1 plus j omega by omega c. So, if you could somehow produce a filter with this kind of quadratic denominator in the transfer function, you can actually chain them together to produce this Butterworth filter of order 7 like this. Basically, you will have to put in 3 filters one after the other and then end with an RC filter which will produce the standard 1 plus j omega by omega c. Of course, you have to choose R and C appropriately so that omega c comes out to be the value 1 by RC that you want. One major assumption that we have made here is that the succeeding stages do not load the previous stages, so that the transfer function of each stage is not affected by what you are connecting to them. And this is what we are actually going to use. This is why what we really need to use are op-amp based filters, which can help you to isolate both the input and the output, using the very fact that op-amps provide huge input impedance and tiny output impedance. So how would we go about implementing these individual pieces? The 1 by 1 plus j omega by omega c piece is something we already understand. That's something we can get using just an RC filter. But what about the other quadratic pieces? And for that, what we need to take a look at is this very special kind of filter, is a very important kind of filter called the Saline K filters. The Saline K filter is a simple op-amp based filter circuit which uses a single op-amp used in the linear region, and the circuit for that looks like this. This is one variant of the Saline K class of filters. There are other similar circuits which do the same job, and they are also called Saline K filters in the literature. Now, how do we analyze a circuit which looks like this? Once again, assuming that the op-amp is working in the linear region, the analysis is really rather simple. Given the output voltage here is VO, the input to the negative and the positive terminal, both of them, assuming that the op-amp is in the linear region, and hence your virtual ground or virtual short, whatever you call it, must be equal to VO into RB by RB plus RA. So just the series potential division formula. So it must be a VO divided by a factor K. And this K, of course, is a factor which is bigger than 1, depending on how big RA is compared to RB. Okay. So now what we have is a situation like this. This node is connected to Vi through R on this side, is connected to VO through this capacitor on that side, is connected to this voltage which is a plus input, hence VO by K through this R. So if you just forget about the op-amp and this RA-RB right now, just focused on this node, the current, the voltages and currents involved would be something like this. So this is the node that we were talking about, is connected to VO through the capacitor, to VO by K through this resistor, and of course there's a capacitor connected between this point and the ground, and there is this input voltage which is connected to this point through the resistance R. Now, if this voltage is VO by K, it's easy to figure out the current here is just VO by K times the admittance of the capacitor, which is VO by K times j omega c. The same current must flow here. Remember, this end is really feeding into the op-amp's input, and the op-amp draws very little current. So the current here is the same as this. That tells you that the voltage here at this point is VO by K, this VO by K, plus the voltage drop across the R, which gives you VO by K into 1 plus j omega CR. Given this information, if I just used Kirchhoff's current law at this node, what I'm going to end up with is VO by K into 1 plus j omega CR, that is this voltage times all the admittances, 1 by R plus 1 by R, that's a 2 by R here, plus j omega C, minus VO by K, minus this VO by K into 1 by R, minus this VO into j omega C, minus this Vi by R, must be equal to the net current flowing into this node, which is 0. So this is what you get. And after this, all you really need to do is multiply simply through by KR and manipulate things a bit. It takes a very simple amount of algebra after this to be able to express VO in terms of Vi. And the VO by Vi ratio just works out to be k divided by 1 minus omega square by omega c square plus 3 minus k into j omega by omega c. So this exactly has the quadratic form for the denominator that we were looking at. There's an extra multiplying factor of k in the numerator, but that of course does not affect the frequency dependence. So just by choosing k appropriately, you can essentially get any one of the quadratic factors that you need in the Butterworth filter. So this k is nothing but this ratio Ra plus Rb by Rb, and by adjusting that you can actually implement any one of the factors that you need in Butterworth polynomials, and thus by chaining such circuits together, what you can do is you can actually end up producing any Butterworth polynomial you want. In fact, you can also use the Saline K topology, this particular connection, to produce other kinds of filters besides the Butterworth filter, but that's a huge topic and we are not going to go into the details here, simply because we don't have time to cover all of that. But I hope I've been able to give you an impression of how useful op-amp circuits can be and how many different things you can make just by using the op-amp and some simple combinations. What I would also like to emphasize and really impress upon you is that analyzing such circuits is really not very difficult. All you have to do is, if it's a linear circuit, use the principle of virtual ground and then use the fact that the op-amp draws no current at its input, and finally just use Ohm's law or Kirchhoff's laws. And most of the time the analysis can be done almost in your head. In the next video, we are going to take a look at one more circuit which has the op-amp at its heart. We have already discussed this once before in a discussion class, but we need to take a deeper look at this. This is the op-amp based oscillator, the Wien bridge oscillator. We will talk a bit more about general oscillator theory, and if time permits, we will take a look at a few other oscillators besides the Wien bridge one. Goodbye till then.